here we go. Hello and welcome back to Calculus 2. We are starting chapter 7 on logarithmic functions, exponential functions, and more. Only 4 sections, so it's a short chapter. And you might want an exam after this, I don't know, we'll see. Not after this class or lecture, but after this chapter. So relax, no need to panic yet. Actually, no, panic. Start, because you're not gonna start learning stuff day before. Let's talk about logs. A log. All right. It's a log. Some of you already seen this, so you can go into hibernation. 2 plus 3 is? 5. Very good. We're done for today. Now, 5 minus 3 is? And 5 minus 2 is? Excellent skills. Next one. 2 times 3 is? 6 divided by 3 is?
2.
And 6 divided by 2 is?
3.
Nice. So what is multiplication? Multiplication is the fast repeated addition. So instead of going into, let's say, 5 plus 5 is 10, plus 5 is 15, plus 5 is 20. You can just memorize the shortcut 5 times 4 is 20, and you're done, instead of adding. So multiplication is not a fundamental operation. It's a lazy way out of repeated addition. So do you have to know multiplication? No, right? If you are going to sit there and add 7 eighths, right? 7 number 8s, not 1 8, but 8s. If you're going to add the number 8 7 times, right? You can do that, and you don't need to memorize. Now, it's the trade-off where you memorize multiplication tables so that you don't have to do repeated addition many times. So multiplication is the fast addition. And now we go and look at the 2 cubed, which is equal to 8. And what is the cube root of 8? 2. And how do I retrieve 3? How do I retrieve the 3? The log. This is where it fits. The log base 2 of 8 is 3. So what is a log? It's a mathematical operation, just like addition or subtraction, right? Now, the reason why you discriminate against it is because it doesn't have a cute symbol. It has letters, so it's immediately, right? But you have addition, you have subtraction, you have multiplication, division, you have exponents, you have the roots, and logs. So they're all on a pile of mathematical operations that you can perform between 2 numbers to obtain a third number. So log is just another operation that happens in between 2 numbers to produce a third number in the pile. And we see which way it fits in this grand scheme of things. So we have addition and subtraction on one pile. Then you say, okay, fast addition is called multiplication, so we're going to have the way to undo it with division. And then we have the uber fast addition, which is fast repeated multiplication, which are exponents, right? And so there are ways in obtaining all of these values. So now, logs are mathematical operation between 2 numbers. It's not a function. Now, how do we create functions? Well, you go to any of these. You can go here, you can go here, you can go here. Doesn't matter where you go. And good evening. And we replace one of the numbers with a variable, and you create a function. So we can go to 2 plus 3 and make it x plus 3, and now it's a linear function. We can go at 6 divided by 3 and call it 6 over x, and now it's a rational function. You can go here and say cube root of x, and it becomes a radical function. So if you go into a log and go log base 2 of x, it becomes a logarithmic function. So logs are not functions out of the box, right? That's not what it is. It's operation between two numbers. You can create a function by replacing that number 8, right, with a variable x, in which case it becomes a function. So that's where the logs fall with calculation and arithmetic and algebra in terms of functions. So now what I'm going to do is say that f of x is equal to log of some base a of x, and we are going to take that as a function. So as soon as you provide the value for x, it stops being a function and it becomes a number, just like anything else. So if I have log base 3 of x is equal to y, that's going to be a function. Now if I go and I say log base 3 of 27, or actually I'll do 125, that is a number. That's a number. It's equal to 5. Because, no. I wanted to say base 5. There we go. Much better. That's equal to 3. There we go. Fix that. So if both numbers are provided, it's just the calculation, then it's equal a number. But if you have a variable in it, right, the input-output variable, then it's a function. It's very simple. The graph for logs goes through 1. It has the vertical asymptote at x equals 0, which is the y-axis. X-intercept at 1, 0. It's always increasing. So those would be some of the basic specs of the graph. And the most famous log that we use is the natural log, which is the ln, and then also the log with the base 10. So what do we have? If your base is e, then we have a lazy notation for it. It's just a lazy notation. And if the base is 10, we just write log x. So in your calculator, you have ln button and you have log button. Those are the two that are used. All of the nature and engineering and all that stuff, it's going to be either base C, like charging battery, and a lot of stuff for electrical engineering and so on, and some stuff for mechanical engineering, obviously. Well, engineering in general, that's going to be ln based. And then you're going to have some things in physics like intensity of, the decibels for sound, or the earthquake, right? So waves in particular would have base, log base 10. Also pH values that you use in chemistry and so on also have a formula that has log base 10 in it. So you guys are either going to look at logs base 10 or log base C, which is ln. Anything else we technically don't care about. And your calculators, your scientific calculators, might have both of these or only one of these, because there is a very easy formula that converts log bases, and you can go from any base into any base easily. So that's called a change of base. Here, let's do a blue. Change of base. And the change of base formula says that log base A of B is log B over log A, or ln B over ln A. So you can convert the base. So if you are in a calculator trying to compute log base 4 of 17, you won't be able to type this in this form. So you will go and you will use ln 17 divided by ln 4. And then make sure you put the parentheses properly, and you should be fine. So ln 17, close the parenthesis, divided by ln of 4, close the parenthesis, for the approximately 2.04373. With logs, try to keep at least 4 decimals to have some decent precision, right? So 4 decimals should be fine. Obviously, I put 5, I'm overachiever, right? But you just put 4. And those would be the very, very basics of what the log is, as not connected to anything, just a log. Now, there are some cute things that you can do with logs. There are these formulas that you should have memorized in your Calc 1 because of the logarithmic differentiation, which says that log base A of xy is, anyone? Very good. Log ax plus log ay. Log ax over y is log ax minus log ay. 3. Log ax to some power p is p log base A of x. So those are the cool formulas. What else can we write? Let's see. Oh, log any base of 1 is equal to 0, and log A of A is equal to 1. So this one has a different form of ln 1 is equal to 0, and this one says that ln of E is equal to 1, because ln, remember, is log base E. So E, that will be the same value, and then the answer is 1. These pop up a lot in your calculation of definite integrals. So you want to really remember these. Need for calculations. So this is the most basic idea, and now the most important formula of all is the one that connects the realm of exponential functions and the realm of logarithmic functions, because they are inverses of each other. So, conversion. A raised to the B equals C converts into log base A of C is B. Too much? Gotta put the barbed wire around it. What happened? Oh, I'm gonna hit it with a rainbow now that you mentioned. Here we go. Where's the rainbow? Boom. Now we're talking. What happened?
We should probably remember that.
Sean says it'll probably never come up again.
Chances are it will never come up, yeah. So this is a single principle which solves all of your equations. If you have exponential equation, you will use the conversion to transform it into logarithmic and solve quickly. If you have a logarithmic equation, you will use this formula to convert it into exponential and solve quickly. So all of the equations that are exponential and logarithmic equations are using this formula to solve, which means 100% of our problems with these are using this formula. So it might come up as you look into all of the homework problems. An example. First, just mathematical gymnastics. No meaning to this, just pile of numbers. Nonsense, right? So 3e to the 6x is equal to 17. So we are supposed to solve this. Well, our goal is to fish out the value of x, right, to solve the equation. And what would be the first step? Yeah, exactly. Divide by 3. Good. So we divide both sides by 3. We have e to the 6x is equal to 17 divided by 3. Keep a few of these decimals. So that's 1 short of 18, right? So there will be 5 2/3. So 6, 6, 6. 7. Now, we have exponential equation. Now, you probably memorized ln both sides to kill e. Yeah, you can do it, but you can also understand that e is the base. So what you can do is you can assign, right? You can use this formula here to convert, because you have now that a is e, b is 6x, and c is 5.6667. That's what you have. If you compare apples to apples. So once you have a designation for your A, B, and C, you can compile the other side, which is the log side, using those A, B, and C. So I have log base C of C, which is 5.6667, is equal to 6x. Now, log E, we know that's ln, so it's ln of 5.6667 equals to, and I'll just divide by 6. So we can quickly now calculate x. Remember the 4 decimals in your answer. So what do I have? ln of 5.6667 close parenthesis divided by 6, x is equal to 0.2891. 891. Now, let's say you care and you want to check. You will take the x and you will plug x where x belongs in the original equation right here. So check. 3 times e to the 6 times 0.2891. This better be very close to 17. Otherwise, we have to go back and redo everything. So 3 times e caret, open parenthesis, 6 times 0.2891, close parenthesis. What I see is 16.99998.206. This is the calculator value. Well, I'm just going to call this 17 because it's good enough. Clearly, you can't get the exact value because you rounded few times. First time when we divided by 3, this is exactly 2/3. But 2/3 is giving us this repeated 6 forever. I put the 7 over there and chopped off and introduced error. And then anytime you have the calculator used for either E or ln, that's going to introduce more error. So clearly we can't get exactly 17 back. But this is pretty good. So we should be happy with this answer. Now, can you use your good old ln both sides to kill E? Yes. Right? And look what happens. When you kill E, you get what? You get this step, which is the conversion step, right? 6x equals to log base C, which is ln E. So you can either use the conversion all the time, or you can use the ln both sides. Whatever makes you happy. So now that we reviewed our exponential logarithmic equations and things, we can go and define some of the stuff. So here we start Calculus 1 lecture, or Calculus 2 lecture. So definition for the natural log. What is the definition of ln x? So ln x is equal to the integral 1 to x of 1 over t dt. We can run calculation to check this. When you integrate 1 over t, you will get ln absolute t, calculated from 1 to x. And when you plug in values, you get ln x minus ln 1. We said that ln 1 is 0. You'll just get ln x. Now, you might ask, what happened with absolute values? Well, observe that this is positive 1 going to some x that is higher than this, which means this x is already positive x. So we don't need absolute values. And there's the answer at the end. I can write x larger than 0, but it should be implied because this is the lower limit, as I said, and this is the upper limit. So x is bigger than 1, which means x is positive, bigger than 0. Which means that we don't need absolute values because it's always already positive. So that will be the definition for the natural log. And now you can be fancy, and you can prove identities. You can prove these formulas, the red ones, using this definition for the log. When you run integral, and then you can prove any of these using that. It's really cool. Since this is not a course in proofs, right, not the honors one, we don't have to worry about it, but the proof is in the book for one of them, ln xy, and then they challenge you to do the other ones, which is great. So let's talk about derivatives that include the ln. So the basic derivative of just ln x is 1 over x. Very good. But we would like to have a better formula than this, because generally that's some kind of function, not x. So how about the derivative of ln of some function f of x? Excellent. So f prime over f itself. And now, let's say that you want general base B. So this would be the boss of all formulas, right? So what do we have? We have the same, which is f prime of f over f of x, and then times 1 over ln b. So this is the boss formula. And you might see this like twice. This formula you are going to see all the time. That's the one that you have to know if someone shakes you out of bed at 4:15 a.m. and says, what's the derivative of sine x? Negative tangent immediately, right? Huh? Oh, no, positive. Hey, it's something. Who cares? So, derivative of ln of sine. Sine, you get control C, control V, right? So that's sine, its derivative on top, cosine, cosine divided by sine is what? Cotangent, right? Cotangent. ln of a cosine over here, cosine goes down, the derivative of cosine is negative sine, so that's negative tangent. Okay, I know it's one of them. Whatever. So most of the time, guys, you are using this formula here. And it's so simple. Anytime you see ln and f of x is that's the formula that works. And this is a rare formula to see because it will require log base 5 of cosine x. No works. All right? It can be done. And all it is the same as this one, except we just have the 1 over ln 5 in addition to. So this is the most general case you can get, but for all of your problems, this formula is the one that you will use. And that's logs. I hope you're not disappointed. Let's talk about exponential function, which is the inverse of logarithmic. So for exponential function, we have y equals b to the x, let's say. Most famous one is e to the x, obviously. The graph would look like this for, let's say, e to the x. And we say exponential growth. And you have the one that looks like this. This is e to the minus x, known as the exponential decay. There are countless examples of use, right, for these. I already told you about the charging and discharging battery for your cell phones or a car or whatever. So if there is a charge battery, you will use this. I think I have a project question on it somewhere. Charging an iPad or something. I'll have to dig up. See. The one for the decay, it's very important. Decay of garbage is important because we bury all of the garbage that we generate. Imagine the amount of garbage. If your household is producing 1 or 2 of those black bags a week, times the number of households in a town, times the number of towns, times the number, right? Those are piles and piles and piles. And plastic tends to stick around, right, for a very long time. Half-life of 10,000 years, meaning to decay half of its mass through alpha radiation. It takes forever. This thing would take 10,000 years of decomposition to become that. Yeah, 10,000 years. So that's plastic, plastic bags and everything that, you know, animals don't get to carry around for some time. Wildlife. And then radioactive decay. One of the myths that, you know, electric car is green. No, it's not green. It's as dirty as the other one, because the electricity that we have is produced where? Thermal plants and thermonuclear plants. Yes, and the nuclear plant produces the nuclear waste, which we conveniently stuff in a mountain, right? And then it leaks. Or throw it in the ocean, and then it leaks. Like, no matter where we put it, it always leaks. So nuclear fission produces huge amounts of nuclear waste, which we don't really shoot to space because it's too, that would be the best solution, but it's too expensive, and we bury it, and then it leaks. So to look at that radiation and how long would it take, right, to go to the levels that are manageable by humans and animals and so on, we use exponential decay. Then carbon dating using the isotope C14. You can figure out how old would something that was organic, how old it is. You can't carbon date stone. So all of the pyramids in Egypt, they can't come to consensus of what's going on there because you have geological data is not matching the data of carbon dating, and carbon dating you can't really do on its own. So it's a whole mess. But if you find a painting, like they found a painting that looked like it was Leonardo, and they say, okay, scrape a little part of paint that was all paint at his time was made out of flowers, that's organic. You can do carbon dating on that and pinpoint very accurately which period was the paint made in, and then like going down to a couple of years precision, which is very amazing that we can do that. So that will be our exponential decay. You can grow money in the account. You can grow population of humans and rabbits and bacteria. That will be the other side, the exponential growth. And then I said both of these would be used in engineering. Cool thing for oscillation, for the motion. You all know that if you just draw sine x, those of you are going in the differential equations. Hello? Right? You have your sine wave, which would be something that looks like that, going in time. Let's use t rather than x. So there will be sine t. Now, we know that when you hang something up for a string and you let it do this, what happened? What happened to it? Is it still moving? No. Let's do the experiment again. Oh, I need to wait 10, 15 seconds and it stops. Right? Why? Why does it stop? Buoyancy, right? Gravity, right? So the graph for something like that would look like you knock it off, so it goes whee, and then it dies out. How do you achieve that? Mathematically, you still, well, now we're going to put the cosine there because we're starting at starting there, let's say. So you put e to the negative t in front, and that kills it in time. It's called oscillation with dampening. So this is how you mathematically model a wave. So if I am to do this somewhere in deep space, this thing will be going on forever, right? Because there will be no gravity if you are sufficiently far from gravitational pull of stars and so on, which you can actually get in between galaxies and stuff. So sure, it would go on this way, right? Just knock it and then it's going to go like that forever. But here, right, it's going to stop. And you saw that experiment I already showed you twice, that it stops. So exponential functions are used in those situations. So now we want to review the derivatives for this. So we have the derivative of e to the x is e to the x. That's not what we usually are after. We are usually after e to the some function, which is itself times the derivative. It's a basic chain rule. And this would be the formula that you are going to be using 99% of the time. Now there is a boss one again, which is b to the f of x, right? Which would be b to the f of x times f prime of x times ln b. So this is the boss equation, because you are free to have any base and you are free to have any function in exponent. So that would be the general case. But again, you are here for 99% of our problems in engineering and so on is going to fit that second line. So useful, the most useful, and then mathematical gymnastics. Look what I can do. Can't find any examples for it outside of the homework, but I can still do it, right? That's it. Bye.